On February 8, 1992, a spacecraft arrived at Jupiter with no intention of staying there. Ulysses had not been sent to photograph the Great Red Spot, map the moons, or search the planet's radiation belts. Jupiter was not its destination. Jupiter was the only available machine large enough to make the turn. For 16 months, Ulysses had traveled outward from Earth along the same broad plane, followed by the planets. Then, during a single, carefully aimed encounter, Jupiter's gravity bent its path into a direction no rocket of the time could have reached economically. The spacecraft left the giant planet falling south of the familiar planetary plane on its way towards the unexplored high latitudes of the Sun. Years later, it would cross above the opposite pole. It became the first mission to examine the heliosphere from that perspective, not because engineers had built an engine powerful enough to force the maneuver, but because they had arranged for an entire planet to do it. That distinction reveals one of the least intuitive rules in spaceflight. Distance is not always the expensive part. Sometimes the most punishing demand is simply changing direction. From Earth, the solar system looks open in every direction. There is no physical wall above the planets. No atmosphere has to be crossed after launch. No ring of debris seals the system into a disk. A spacecraft can point its antenna or its camera toward the north ecliptic pole as easily as it can point toward Mars. Yet pointing is not traveling. The vehicle may turn its body with small thrusters, but its orbit continues along the old path. To redirect the path itself, the engines must change the spacecraft's velocity. And velocity includes direction as well as speed. That is where ordinary intuition fails. Earth moves around the Sun at an average speed of about 29.8 kilometers per second. A spacecraft launched from Earth inherits nearly all of that heliocentric motion before its own mission has truly begun. In the Sun's frame, it is already racing sideways around the star at more than 100,000 kilometers per hour. Mission designers usually treat that motion as an asset. A departure toward Mars, Jupiter, or the outer solar system is planned around it. The spacecraft does not begin from rest. It begins aboard a moving world, and the launch is timed so that Earth's orbital velocity helps create the required solar orbit. But suppose the destination is not ahead, behind, inward, or outward along the planetary plane. Suppose the objective is to climb almost directly above it. The inherited velocity does not disappear when the rocket points north. The spacecraft can add an upward component, but it keeps the sideways component it already had. Its new path becomes diagonal. To make the trajectory steep, the mission must rotate a velocity vector that is already nearly 30 kilometers per second long. That is not a matter of steering in the way an aircraft banks through air. There is no surrounding medium to push against. The only practical way to turn the orbit is to produce a new velocity vector with propulsion, a gravitational encounter, or some other external force. The cause can be expressed with a simple idealized comparison. Imagine a spacecraft already moving around the Sun in a circular orbit at Earth's distance, free of Earth's own gravity, and ready for one instantaneous maneuver. To turn its velocity by 90 degrees while keeping the same speed would require a velocity change of roughly 42 kilometers per second. It would not literally stop and start again. The maneuver is the vector difference between the old motion and the new one. But the result is still enormous. Now compare that with solar escape. At Earth's distance, the ideal escape speed from the Sun is about 42 kilometers per second. The spacecraft is already moving at nearly 30. If it accelerates in the direction it is already traveling, the additional speed needed in that simplified case is only about 12 kilometers per second. Real missions must also escape Earth, survive launch losses, and follow trajectories far more complicated than this clean calculation. Even so, the comparison exposes the contradiction. Rotating an orbit through a right angle at 1 astronomical unit can demand more than 3 times the ideal velocity change required to push the same orbit onto a solar escape path. Leaving the Sun can be cheaper than turning sideways. This is not because the solar system has a preferred direction written into space. It is because nearly every useful object in the system shares a history of motion. The major planets orbit close to a common plane. Earth launches spacecraft from within that plane. The planets that can provide gravity assists also travel within it. The transpatient network is already moving sideways, and every practical mission begins as part of that flow. The result is an invisible geography. Some destinations are far away but dynamically convenient. Others may be empty regions with nothing blocking the route, yet they remain difficult because reaching them requires fighting the motion a spacecraft received for free. Ulysses demonstrated the only economical solution available in its era. Instead of attempting the plane change near Earth, where heliocentric speed is high, the mission traveled outward to Jupiter. Farther from the Sun, orbital motion is slower, so changing its direction is less costly. Then Jupiter supplied the decisive bend. The planet's gravity redirected the spacecraft into an orbit reaching more than 80 degrees of solar latitude. Ulysses did not fly straight above the Sun and remain there. It followed a long, elliptical path, repeatedly moving from one high-latitude region to the other. But it crossed into a part of the heliosphere that previous spacecraft had observed only indirectly. The price was time, geometry, and dependence on a world hundreds of millions of kilometers away. More than 3 decades after that encounter, the problem remains. Solar Orbiter is now raising its view above the solar equator, but it is doing so gradually. A Venus flyby in February 2025 increased its orbital inclination to about 17 degrees. Another encounter, scheduled for December 2026, is intended to raise it to roughly 24 degrees. The spacecraft is not making one heroic turn. It is accumulating small changes through repeated planetary encounters, trading years of mission duration for propellant it does not have to carry. That is the pattern we will follow. Not the vague question of why spacecraft cannot go up because they can. The more precise question is why a direction with no wall, no atmosphere, and no obvious obstacle can become one of the most expensive directions available. Answering it requires rebuilding the solar system as a map of velocity rather than a map of places. On the familiar map, the Sun sits in the center, the planet's space rings, and empty space surrounds them. On the map used by mission designers, every point is moving. Earth arrives at a launch date with a specific velocity. Jupiter reaches an encounter with another. A spacecraft is never sent merely to a location. It must arrive there with the right speed and direction, and those two requirements often cost more than the distance itself. The central constraint is not that rockets are too weak to move through empty space. It is that rockets must carry the propellant needed to alter motion, while the amount of propellant grows with the mass that must be accelerated, including the mass of the additional propellant. A demanding maneuver adds fuel. That fuel requires a larger stage. The larger stage requires still more energy to launch. The penalty compounds until a trajectory that is mathematically possible becomes operationally useless. Gravity assists, electric propulsion, solar sails, and maneuvers performed far from the Sun can change that calculation. None abolishes it. Each trades one resource for another: fuel for time, engine power for distance, direct control for planetary alignment, payload for velocity. The turn made by Ulysses therefore opens a larger investigation. We need to understand why the planets share a plane, why Earth gives every departing spacecraft a powerful sideways inheritance, why a change in direction becomes cheaper when the spacecraft slows down, and why the best solution may involve traveling billions of kilometers away from the direction you ultimately want to reach. The solar system is not difficult to cross merely because it is large. It is difficult because everything inside it is already moving, and the motion cannot be negotiated away. Before a spacecraft can go anywhere, it must first solve the orbit it already has. The orbit a spacecraft inherits from Earth is not an accident of launch geography. It is the surviving motion of a structure that began forming before Earth existed. More than 4.5 billion years ago, the material that would become the suns, planets, moons, asteroids, and comets occupied a diffuse region of gas and dust. It was not a finished disk. It was a cold, irregular cloud, disturbed neighboring stars, magnetic fields, and the motions of countless particles traveling in different directions. Yet the cloud possessed a small amount of overall rotation. At first, that rotation may have seemed insignificant. The material was spread across an enormous volume, and the cloud turned slowly, but gravity began drawing it inward. As the cloud contracted, its rotation accelerated. The principle is familiar in a smaller setting. A spinning skater rotates faster after pulling their arms toward the body. The skater has not created rotation from nothing. The same angular momentum has been concentrated into a smaller distribution of mass. A collapsing cloud follows the same rule. As its radius decreases, its rate of rotation increases. That explains why the early solar system spun faster as it contracted. It does not, by itself, explain why it became flat. A rotating cloud can still contain motion in every direction. Some particles can move with the overall rotation, others can rise above it, fall below it, or cross the center on steeply inclined paths. In the beginning, those motions coexist. The cloud is thick, disordered, and three-dimensional. Then the particles collide. Gas atoms, molecules, grains of ice, and microscopic fragments encounter one another constantly as the cloud becomes denser. During those collisions, motion that does not agree with the cloud's overall rotation is gradually reduced. Two particles approaching the central plane from opposite sides can collide and lose much of their vertical motion. Their kinetic energy is converted into heat, and some of that heat radiates away. The rotational motion is harder to erase because most of the cloud shares it. Collisions can redistribute angular momentum, moving some material inward and other material outward, but the total cannot simply vanish. Motion above and below the emerging plane is damped. Motion around the center survives. Over time, the cloud becomes a disk. This is not a rigid disk like a sheet of metal. It is a dynamic structure of gas and dust with turbulence, spiral features, temperature gradients, pressure, magnetic fields, and material flowing both inward and outward. But compared with its width, it becomes remarkably thin. Most of its mass settles near one shared rotational plane. The young sun forms at the center, where density, pressure, and temperature rise high enough for nuclear fusion to begin. Farther out, dust grains collide and sometimes stick. Small aggregates become larger bodies. Larger bodies attract more material through gravity. The process builds planetesimals, planetary embryos, and eventually planets. Every major planet begins inside the same rotating structure. Their orbital alignment is therefore inherited rather than negotiated. They do not independently discover a common plane after formation. They are assembled from material already moving within it. That distinction matters because the disk leaves behind more than a pattern of locations. It leaves behind a pattern of velocity. The planets orbit in the same general direction because the material that formed them shared the same circulation around the young sun. Most of their orbits remain close to the original disk because the vertical motions had already been damped before the planets became fully assembled. The entire planetary system carries the angular momentum of its origin. Earth is part of that inheritance. Every launch site, every rocket, every payload, and every person standing on the planet is moving around the sun as a consequence of it. When a rocket lifts from the surface, it does not depart from a stationary platform. It departs from a planet rotating on its axis while orbiting the sun, while the sun itself moves through the galaxy. Mission designers choose a reference frame appropriate to the problem. But none of those motions disappears merely because a spacecraft has left the ground. For interplanetary flight, Earth's orbital motion is the crucial. Inheritance, the spacecraft begins with nearly the same heliocentric velocity as Earth. A launch vehicle can add to that velocity, subtract from it, but it cannot choose to begin from zero. This is why diagrams of the solar system can be misleading. A diagram shows positions. Orbital mechanics is governed by states of motion. A spacecraft beside Earth in a drawing may appear free to leave in any direction. In reality, it is already sweeping around the sun. If its engines stop immediately after escaping Earth, it will not hover near the point where the planet released it. It will continue orbiting the sun on a path similar to Earth's. To move toward Mars, engineers do not aim directly at where Mars appears in the sky and hold that direction. They place the spacecraft into a new solar orbit that intersects Mars' future position. To move toward Venus, they reduce heliocentric energy, so the spacecraft falls inward. To reach Jupiter, they increase that energy and arrange an encounter months or years ahead. Every trajectory is built on the existing motion. The flatness of the planetary system makes these transfers efficient. Because the major planets occupy nearly the same plane, A spacecraft can travel from one orbit to another without spending much of its limited propulsion changing inclination. It can devote most of its energy to changing the size and shape of its orbit instead. That is one reason the ecliptic is more than a geometric reference. It is the main transportation corridor of the planetary system. The corridor is not perfectly thin. Mercury's orbit is inclined by about 7 degrees relative to Earth's orbital plane. Venus, Mars, Jupiter, Saturn, Uranus, and Neptune differ by smaller amounts. Asteroids occupy a wider distribution. Comets can arrive on much steeper paths. The outer solar system contains populations whose orbits preserve evidence of scattering, resonance, migration, and ancient gravitational encounters. But the major planets remain sufficiently aligned that spacecraft can move among them with relatively modest plane corrections. That shared geometry enables chains of gravity assists. A mission can approach one planet, allow its gravity to reshape the trajectory, then continue toward another planet that is also located near the same broad plane. Voyager 2's journey past Jupiter, Saturn, Uranus, and Neptune depended on that architecture. The planets were separated by billions of kilometers, yet their orbits occupied a common geometric neighborhood. The spacecraft did not have to climb far above or below the system between encounters. Each planet could pass it onward through the same broad corridor. A mission attempting to move far out of that corridor faces a different problem. Once it has climbed away from the planetary plane, most of the useful massive bodies are no longer positioned along its route. The planets cannot provide repeated assists if the spacecraft is traveling where the planets never go. Leaving the plane therefore creates two costs. The first is the direct velocity change required to alter the orbit's inclination. The second is the loss of future opportunities to borrow momentum from planets. These costs reinforce each other. A spacecraft needs more propulsion because it is leaving the region where gravity assists are easiest to obtain. As the trajectory becomes steeper, the planetary system becomes less useful as a transportation network. Jupiter is the major exception because its mass allows one carefully designed encounter to produce a large deflection. Even then, the spacecraft must reach Jupiter first, and the geometry of the flyby must be correct. The planet cannot redirect a mission toward any arbitrary path at any arbitrary time. The encounter depends on arrival speed, approach direction, altitude, planetary position, and the final orbit required after departure. Ulysses succeeded because engineers treated Jupiter not as a destination, but as part of the propulsion system. The mission exploited the same shared planetary plane it intended to leave. It traveled through the corridor before using the largest available world as an exit ramp. The deeper lesson is that the solar system's flatness is not merely visual. It organizes what is easy, what is expensive, and what remains unexplored. Most spacecraft follow the ancient disk because the planets follow it. The planets follow it because the material that built them had already lost most of its motion in every other direction. The original gas has dispersed. The dust has been incorporated into worlds or scattered into space, and the young sun has long since entered middle age. Yet the rotational pattern remains. The vanished disk still controls the routes. It determines which directions come with inherited speed, which planets can be reached efficiently, which gravity assists are available, and which scientific targets require years of indirect travel. A structure that no longer exists as it once did continues to shape every interplanetary mission through angular momentum alone. Before we can understand how to escape that structure, we have to measure the penalty for turning away from it. And that penalty depends not only on the angle of the turn, but on where the spacecraft attempts it, how fast it is moving, and whether it can afford to trade distance for a slower place to change direction. A spacecraft does not pay for distance in the same way a car pays for miles. It pays for changes in velocity. That difference is easy to miss because speed and direction feel separate in ordinary life. A car can turn a corner without first erasing its forward motion. Tires push against the road, and the road supplies the sideways force. An aircraft banks because its wings redirect airflow. A ship turns because its rudder pushes against water. A spacecraft has none of those supports. Once its engines stop, it follows the path created by its current velocity and the gravity acting upon it. Turning the vehicle's nose changes where the antenna points. It does not automatically change where the spacecraft is going. To bend the trajectory, the spacecraft must apply force over time. That force creates a change in velocity known as delta V. The term includes any change in speed, direction, or both. A spacecraft that accelerates from 10 to 11 kilometers per second has used 1 kilometer per second of delta V. A spacecraft that keeps the same speed but turns onto a different heading has also used delta V, sometimes much more than expected. The cost of a plane change can be described by a compact relationship. If a spacecraft is moving at speed v and rotates its velocity through an angle I without changing the final speed, the required delta v is twice the speed multiplied by the sine of half the angle. For small turns, the cost grows gradually. A 1-degree correction at Earth's orbital speed requires roughly half about 2 seconds. 10 degrees approaches 5.2. 10 degrees approaches 5.2. Those are already serious numbers in spacecraft engineering. Many interplanetary vehicles carry only a fraction of a kilometer per second for major corrections after launch. At 30 degrees, the idealized cost rises to more than 15 kilometers per second. At 60 degrees, it is nearly 30. At 90 degrees, it reaches about 42 kilometers per second. The spacecraft would still be traveling at roughly the same speed after the maneuver. Nearly all that propulsion would have been spent changing the direction of motion rather than increasing its magnitude. This is why a right-angle turn in space cannot be understood as simply pointing a rocket upward. The old orbital velocity and the desired new velocity form two sides of a geometric problem. The engine must bridge the gap between them. Imagine two arrows of equal length drawn from the same point. One points horizontally, the other points vertically. Each represents a velocity of nearly 30 kilometers per second. The required maneuver is not the length of either arrow. It is the diagonal connecting the tip of the first to the tip of the second. That diagonal is longer than either component alone. The comparison with solar escape is revealing. In an ideal circular orbit at Earth's distance, a spacecraft travels around the Sun at nearly 29.8 kilometers per second. The local escape speed is about 42.1. Accelerating in the existing direction, therefore, requires an additional 12.3 kilometers per second to reach the escape threshold. A 90-degree plane change at the same location requires approximately 42.1 kilometers per second. In that simplified case, turning the orbit through a right angle costs more than 3 times as much as escaping the Sun. The spacecraft leaving the solar system is not overcoming all solar gravity in one sudden act. It is increasing its orbital energy until the resulting path no longer closes. The Sun continues slowing the spacecraft as it travels outward, but never enough to pull it back. The spacecraft making the plane change is solving a different problem. It must replace a large existing sideways motion with another motion aimed into a new plane. Its original orbital energy is not useless, but much of its direction is. The penalty becomes even more severe when propulsion is considered. Chemical rockets must accelerate not only the spacecraft and its instruments, but also the propellant that will be burned later. Additional delta V requires additional propellant. That propellant adds mass, which requires more propellant to accelerate. The relationship is exponential rather than linear. A mission designer cannot double the maneuver simply by doubling the fuel tank. The governing relationship is the rocket equation. The achievable change in velocity depends on the exhaust velocity of the engine and the logarithm of the ratio between the spacecraft's initial mass and its final mass after propellant has been consumed. For a high-performance chemical stage, a delta V of several kilometers per second may demand a large fraction of the vehicle's mass in propellant. At tens of kilometers per second, the required mass ratio becomes extreme. Tanks, engines, insulation, guidance systems, and payload all occupy part of the mass budget. The mathematical solution may leave almost no room for the spacecraft itself. This is where a trajectory changes from difficult to impractical. A direct 90-degree solar plane change near Earth would not merely require a large rocket. It would require one stage to carry the fuel for a maneuver, whose own fuel mass creates the need for still more fuel. Even staging would not make the mission attractive when other routes can let gravity provide much of the deflection. The obvious response is to perform the turn where the spacecraft is moving more slowly. Plane change cost scales with speed. The same angular change is cheaper when the velocity vector is shorter. Objects orbiting close to the Sun move rapidly. Earth circles the Sun at nearly 30 kilometers per second. Jupiter's circular orbital's speed is about 13. Neptune's is a little more than 5. An idealized 90-degree change at Jupiter's distance, using the local circular speed, would cost about 18.5 kilometers per second. At Neptune's distance, it would be roughly 7.5. The price of the same turn falls dramatically as the maneuver moves outward. But the spacecraft must first reach that distant location. It may take years. It may need additional energy to enlarge its orbit. Its instruments must survive the cruise. Its power system must function in weak sunlight, or it must carry a long-lived nuclear source. Communication delays grow, data rates fall, and the mission spends much of its lifetime traveling away from the region it ultimately wants to observe. Distance becomes a tool for reducing velocity, but that tool has its own cost. There is also a way to make a plane change cheaper without traveling to a different planet. A spacecraft in an elongated orbit moves fastest near the Sun and slowest at its farthest point. If it first raises the distant end of the orbit, performs the inclination change there, and then adjusts the orbit again, it can make the turn at a lower speed. This strategy replaces one expensive maneuver with several smaller ones. Whether it saves delta V depends on the desired inclination, the size of the orbit, and the propulsion available. For large plane changes, especially when time is less important than fuel, the indirect route can be far more efficient than turning immediately. The principle appears throughout mission design. Do not make an expensive change while moving quickly if the orbit can first carry the spacecraft somewhere slower. Ulysses followed an extreme version of that logic. It traveled outward before receiving its decisive deflection. By the time it reached Jupiter, the geometry of its motion had changed from the conditions near Earth. Then Jupiter supplied the force that onboard engines could not. The flyby did not eliminate conservation of momentum. The spacecraft exchanged momentum with the planet. Jupiter's own orbital motion changed by an immeasurably small amount, while the far lighter spacecraft experienced a major alteration in its heliocentric trajectory. From Jupiter's perspective, Ulysses approached, accelerated into the planet's gravity well, curved around it, and departed with nearly the same speed relative to Jupiter that it had arrived with. From the Sun's perspective, the direction and energy of the spacecraft's path changed because Jupiter itself was moving. A gravity assist is therefore not a free engine. It is an exchange with a moving planet. For an ordinary outward mission, the exchange is arranged to increase heliocentric speed. For Ulysses, the crucial result was a steep change in direction. The flyby converted a trajectory lying close to the planetary plane into one that crossed the Sun's high latitudes. The planet performed a plane change whose propellant equivalent would have overwhelmed the spacecraft. This reveals the true scale of the obstacle. The difficulty is not measured by the emptiness above the ecliptic or by the number of kilometers between the spacecraft and some imagined upper bound. It is measured by the separation between two velocity vectors. That separation can be enormous, even when the spacecraft remains at the same distance from the Sun. A destination may be physically nearby but dynamically remote. Another may be billions of kilometers away, yet reachable through a sequence of orbits and gravity assists that work with the motion already present. Orbital mechanics does not ask only where the spacecraft must go. It asks what velocity it must have when it gets there, what velocity it has now, and how the mission will cross the difference without consuming itself in the attempt. Once that is understood, the apparent freedom of empty space becomes more constrained. Every direction remains open, but they do not carry equal prices, and the most economical path toward a place above the planets may begin by traveling outward through the very plane the spacecraft intends to leave. The spacecraft approaching Jupiter is not merely falling toward a massive object. It is entering a moving gravitational system. That motion is what makes the encounter useful. If Jupiter were fixed in space, a spacecraft could fall toward it, accelerate, curve around the planet, and climb away again. Neglecting losses, it would depart with nearly the same speed relative to Jupiter that it had before the encounter. Gravity would change the direction of the path, but it would not provide a lasting gain in energy. Jupiter is not fixed. It is moving around the Sun at roughly 13 kilometers per second. A spacecraft passing through its gravity can exchange momentum with that moving planet. Depending on the approach geometry, the vehicle can leave with more heliocentric speed, less heliocentric speed, or a radically different direction. The planet becomes a moving lever. The exchange is real, even though the effect on Jupiter is effectively undetectable. The spacecraft gains or loses momentum. Jupiter experiences the opposite change. But Jupiter is so massive that the alteration to its orbit is vanishingly small. The spacecraft, millions of times lighter, can emerge onto an entirely new solar trajectory. This is the mechanism Ulysses depended upon. The mission approached Jupiter on a carefully selected path that allowed the planet's gravity to rotate the spacecraft's velocity steeply away from the ecliptic. The encounter did not simply accelerate Ulysses outward. It redirected the orbital motion the spacecraft had inherited from Earth. To understand how dramatic that was, consider what a flyby must control. The spacecraft arrives with a particular velocity relative to the planet. That incoming velocity determines the shape of the hyperbolic path it follows to the planet's gravitational field. The closer the flyby, the stronger the bending can be. A slower approach can also be deflected more than a very fast one because the planet's gravity has more time to alter the path. But closeness brings danger. Jupiter is surrounded by an intense radiation environment. A trajectory passing too deeply through the system can expose electronics and instruments to damaging energetic particles. A low flyby also requires exquisite navigation. A small targeting error months earlier can become a major displacement at closest approach. The spacecraft must avoid the planet, its rings, and its moons while arriving at precisely the angle needed for the desired departure. The flyby altitude, arrival direction, encounter speed, and timing all become part of one connected solution. Change Chuan and the final orbit changes. A gravity assist is therefore less like receiving a push and more like threading a moving gravitational needle. The spacecraft does not choose its departure after arriving. The departure is encoded in the approach. Long before the encounter, navigation teams determine where the spacecraft must pass through an imaginary plane near the planet. Small correction burns reshape the arrival path. Radio tracking measures distance and velocity. Each adjustment is modest, but the cumulative goal is exact. Cross Jupiter's moving gravitational field along the one corridor that produces the required solar orbit afterward. Once the spacecraft is close, there is little opportunity for correction. The decisive maneuver is performed by gravity. This is one reason gravity assists can be both powerful and restrictive. They replace propellant with geometry, but geometry cannot be improvised. The planet must be in the right place. The spacecraft must arrive at the right time. The resulting trajectory must be compatible with the mission that follows. For Ulysses, the mission accepted a long trip outward and a harsh encounter environment in exchange for a turn that chemical propulsion could not afford. After Jupiter, the spacecraft entered a solar orbit unlike those of the planets. It moved inward again, crossed beneath the Sun's equatorial region, then climbed to high southern solar latitude. Later, its orbit carried it north. The path was still governed by the Sun's gravity, but its orientation had been rotated almost upright relative to the planetary system. Ulysses had not escaped motion within a plane. It had entered a different plane. That distinction matters. A spacecraft cannot simply move vertically above the solar system and remain fixed there. The Sun continues pulling on it. Unless the spacecraft possesses enough energy to escape entirely, its path must curve. A high-inclination mission still follows an orbit around the Sun, crossing the ecliptic at 2 points called nodes. At one node, the spacecraft travels from below the reference plane to above it. At the other, it descends again. The spacecraft may reach a great distance above the ecliptic between those crossings, but it is never parked above the Sun in an absolute sense. Its height changes continuously as the orbit carries it around. This is where visual language can mislead again. A drawing may show Ulysses looping over the solar poles as though the spacecraft traveled around the Sun in a neat vertical circle. Its actual orbit was elongated. It moved far from the Sun near the outer part of its path. and much faster when passing through inner solar system. The polar observations were episodes within a long orbit, not a permanent station above one pole. The changing speed follows another central rule of orbital mechanics. As a spacecraft falls closer to the Sun, gravitational potential energy becomes kinetic energy. It moves faster. As it climbs outward, it slows. The orbit continually exchanges one form of energy for the other. That creates an opportunity and a constraint. The spacecraft is slowest at the distant end of an elongated orbit, making that region attractive for plane changes. A small thrust applied there can rotate the orbital plane more efficiently than the same thrust applied near the Sun. But a plane chain made far away does not necessarily place the spacecraft over the Sun immediately. It changes the orientation of the entire orbit. The vehicle may then need months or years to reach the part of the new path where the scientific observations are possible. Orbital maneuvers act on future geometry. A burn lasting minutes can determine where a spacecraft will be years later. A flyby lasting hours can define an orbit that persists for decades. Mission design is therefore an exercise in delayed consequence. This is also why combinations of maneuvers can outperform a direct solution. A spacecraft seeking a large inclination change might first increase the eccentricity of its orbit. Raising its farthest point, it coasts outward and slows. At that distant point, it performs the plane change. It may then lower the orbit again or fall naturally toward the region of interest. Each individual step consumes energy or time, but the total propulsion cost can be lower than rotating the orbit while moving rapidly near Earth. The logic resembles moving a heavy object with a long lever. The indirect setup appears cumbersome, yet it changes the conditions under which the hardest part of the work is performed. Planetary flybies extend that leverage. Instead of carrying all the energy needed to reshape the orbit, the spacecraft borrows from the motion of a planet. But not every planet can perform every turn. A small planet produces limited deflection. A massive planet can bend the path more strongly, but only if the spacecraft can reach it and survive the encounter. The orbital plane of the planet constrains the geometry available. Its position controls when the encounter can occur. Its moons, radiation belts, and atmosphere may limit the closest safe approach. Jupiter was uniquely suited to Ulysses because it combined enormous mass with a reachable orbit and enough gravitational authority to produce a steep deflection. Venus offers a different advantage. It is less massive, so each flyby produces a smaller change. But a solar spacecraft can encounter Venus repeatedly. With every pass, the orbit can be adjusted again. The result is not one violent redirection, but a staircase of inclination changes. This patient strategy is visible in solar orbiter's design. The spacecraft repeatedly returns to Venus, using the planet to raise its viewing angle over time. Each encounter contributes only part of the final geometry. The mission gains access to higher social latitudes by surrendering immediacy. One planet provides strength, another provides repetition. The same underlying physics supports both approaches. Electric propulsion offers a third path. Instead of receiving a large change from a planet, a spacecraft can apply a weak force continuously. Ion and Hall effect thrusters expel propellant at much higher velocities than chemical rockets, allowing them to achieve large cumulative changes in spacecraft velocity with relatively little propellant. The thrust is small. The spacecraft may accelerate so gently that the change is almost imperceptible from moment to moment. Sustained for months or years, that pressure can reshape an orbit profoundly. For plane changes, continuous low thrust can be applied in carefully varying directions as the spacecraft travels around the Sun. The engine does not simply point above the ecliptic at all times. Its thrust must be coordinated with orbital positions so that repeated small contributions rotate the plane efficiently rather than wasting energy on changes the mission does not need. The advantage is propellant efficiency. The cost is time, electrical power, thermal management, engine life, and operational complexity. Near the Sun, solar arrays can provide abundant energy, but the spacecraft moves rapidly, making inclination changes expensive. Further out, the spacecraft moves more slowly, but sunlight weakens, reducing the power available to electric engines. A nuclear power source could overcome part of that problem, but it adds mass, cost, and engineering constraints. Every solution encounters another trade-off. Chemical propulsion supplies high thrust but consumes propellant rapidly. Electric propulsion conserves propellant but requires long operating periods. Gravity assists can provide enormous changes without onboard fuel, but only when planetary geometry permits. Traveling outward lowers plane change cost, but lengthens the mission and reduces solar power. There is no maneuver that simply removes the inherited orbit. The path of Ulysses emerged from choosing which penalties were acceptable. The mission spent years reaching the planet that could make the turn. It accepted dependence on a single encounter. It entered a radiation environment that required careful engineering. In return, it gained a solar perspective unavailable from the ecliptic. The real engine of the mission was not one device. It was a chain consisting of Earth's launch motion, the transfer to Jupiter, Jupiter's orbital momentum, the geometry of the flyby, and the Sun's gravity shaping the orbit afterward. Remove any link and the polar mission disappears. That is how extreme trajectories are built. Not by defeating orbital mechanics, but by arranging several parts of it so precisely that the forces already present perform most of the work. The next question is what that unusual orbit was worth. After spending an entire planet to make the turn, Ulysses entered a region no previous spacecraft had sampled directly, and what it found showed that the Sun did not behave the same way in every direction. Ulysses did not carry a camera designed to photograph the Sun's poles. Its most important view was assembled from particles, magnetic signals, dust impacts, and energetic radiation passing directly pass through the spacecraft. That was exactly what the mission required. A photograph can show the atmosphere near the Sun, but the heliosphere extends far beyond anything visible as a surface. It is a vast region filled by the solar wind, a continuous flow of charged particles escaping from the corona and carrying part of the Sun's magnetic field outward. Earth, the planets, and most spacecraft operate inside that flow. Before Ulysses, nearly every direct measurement of the solar wind had been made close to the ecliptic. Spacecraft could sample conditions near Earth or along routes to other planets, but they remained embedded in a narrow range of solar latitude. Researchers were trying to reconstruct a three-dimensional system from observations taken mostly through its middle. The missing dimension mattered because the Sun is not uniform. Its visible surface rotates depending on latitude. Its magnetic field evolves through an approximately 11-year activity cycle. Dark coronal holes can open pathways through which plasma escapes rapidly. Active regions, eruptions, and complex magnetic structures are concentrated differently as the cycle progresses. There was no reason to assume that measurements near the solar equator described the entire heliosphere. During its first southern polar passage in 1994, Ulysses entered a flow unlike the variable wind, commonly measured near the ecliptic. At high southern latitudes, the spacecraft found solar wind moving at roughly 750 kilometers per second. It was fast, persistent, and unexpectedly uniform. Near the equatorial regions during solar minimum, the wind often traveled closer to 350 kilometers per second and changed considerably as different structures rotated past the observer. Above the poles, the flow was more than twice as fast and far steadier. The distinction transformed the map. At solar minimum, the fast wind was not a narrow stream confined directly above each pole. It expanded outward from large polar coronal holes and occupied much of the heliosphere. The slower, more irregular wind remained concentrated around a comparatively narrow band near the solar equator. The Sun's influence was divided into broad regions with different speeds, densities, and magnetic conditions. Where fast wind caught slower material released earlier, the two flows could not pass cleanly through each other. The faster plasma compressed the slower wind ahead of it, creating large interaction regions that rotated with the Sun. These structures could form shocks farther outward and accelerate charged particles. The heliosphere was not simply a smooth wind expanding into space. It contained enormous moving boundaries, created by differences in the wind itself. From Earth's orbit, those structures are encountered near one latitude and at particular phases of solar rotation. Ulysses crossed through them while changing latitude, revealing how their geometry extended above and below the familiar observational corridor. This was the first major consequence of paying for the polar trajectory. Ulysses converted a collection of local measurements into a global system. It also challenged expectations about the heliospheric magnetic field. The Sun's surface field is complex, but at large scales, it behaves partly like a magnetic dipole, with opposite polarities in the northern and southern hemispheres. The solar wind stretches magnetic field lines outward as the Sun rotates, creating a spiral structure throughout interplanetary space. Before Ulysses, researchers expected the strength of the magnetic field, carried by the wind, to vary significantly with latitude. A simple picture suggested that field lines should become more concentrated toward the poles, producing stronger measurements there. The spacecraft did not find the predicted increase. After accounting for distance from the Sun, the amount of open magnetic flux detected in the solar wind was much more uniform across latitude than the simplest models had suggested. The polar heliosphere was not merely a stronger version of the equatorial magnetic environment. Something in the way magnetic fields emerged from the corona and expanded into space was redistributing that flux. This was an expectation violation with consequences beyond one mission. Models of the solar wind must connect conditions near the Sun with measurements made throughout the heliosphere. If the field appeared nearly independent of latitude, far from the Sun, then the geometry close to the corona could not be carried outward in the most obvious way. The observations forced researchers to reconsider how field lines spread, how the solar wind expands, and how measurements from one location should be used to estimate the Sun's total open magnetic flux. Ulysses also tested another apparently reasonable prediction. Galactic cosmic rays are high-energy particles arriving from outside the solar system. Before reaching the inner heliosphere, they must pass through the magnetic turbulence and outward-flowing plasma created by the Sun. That environment deflects and modulates them, reducing how many reach the planets. Researchers expected cosmic rays might enter more easily through the polar regions. The magnetic geometry there appeared more direct. If the field lines offered a straighter route inward, the poles could function as preferred access channels. Ulysses found no large polar increase of the kind anticipated. The high-speed solar wind carried waves and magnetic irregularities capable of scattering incoming particles. Any geometric advantage offered by the polar field was largely countered by the conditions within the wind itself. The heliosphere's defenses could not be understood from field direction alone. The turbulence traveling along those fields also mattered. For spacecraft and future crews, this distinction is not abstract. Galactic cosmic rays contribute to radiation exposure beyond Earth's protective magnetic field. Predicting that exposure requires understanding how the heliosphere changes with position and with the solar cycle. A route above the ecliptic would not automatically escape the radiation environment encountered near the planets. It would enter a different mixture of solar particles, magnetic turbulence, and galactic cosmic rays, all varying with time. Ulysses remained in operation long enough to observe that time dependence directly. Its orbit around the Sun lasted more than 6 years. During its first polar passes, solar activity was near minimum, when the large polar coronal holes produced broad regions of fast wind. During later passes around 2000 and 2001, the Sun was far more active. The clean division between fast polar wind and slow equatorial wind had largely broken down. The magnetic field was reorganizing. Coronal holes appeared at different latitudes. Transient eruptions and irregular flows reached much more widely across the heliosphere. The same trajectory encountered a different Sun. This gave the mission something more valuable than a single polar survey. It produced a three-dimensional view changing through the activity cycle. The heliosphere could no longer be represented as one stable shape with fixed polar and equatorial zones. Its internal structure expanded, contracted, fractured, and reassembled as the Sun's magnetism evolved. Near solar minimum, broad polar regions behaved with surprising order. Near maximum, latitude became a weaker predictor of what the spacecraft would encounter. The contrast also clarified why one observation from one spacecraft can be dangerous to generalize. A detector near Earth samples the solar wind at one location, one latitude, and one moment in an evolving cycle. Conditions measured there may be accurate locally, while failing to describe most of the heliosphere. Ulysses showed how much information had been missing because nearly all previous missions shared similar orbital geometry. That was the scientific return on the difficult turn at Jupiter. The spacecraft did not reach a hidden object. It reached an observational angle. From that angle, familiar phenomena acquired structures that could not be reconstructed confidently from the ecliptic alone. The fast solar wind became a dominant global flow rather than an unusual local condition. The magnetic field became more uniform with latitude than expected. Cosmic rays failed to use the poles as simple entry corridors. Solar cycle reshaped the heliosphere across every latitude rather than merely changing conditions near Earth. Each result came from crossing regions no conventional planetary trajectory would naturally enter. But Ulysses also revealed the limits of a single polar spacecraft. It measured the plasma passing through one point at a time. It could not continuously image the entire polar corona. Its long orbit meant that differences between two locations could also be differences between two times. When it reached the opposite hemispheres, months had passed and the sun had changed. The mission opened the third dimension, but it could not observe all three dimensions simultaneously. That limitation would shape the next generation of solar missions. Some would move closer to the sun. Others would use repeated planetary encounters to raise their inclination gradually. Cameras would attempt to see the polar regions directly, while particle instruments continued sampling the wind. No successor could simply repeat Ulysses with better instruments and expect the same trajectory to be easy. The Jupiter route still demanded years, a rare geometry, and a mission capable of surviving far from the sun before returning inward. The scientific value had been demonstrated. The transportation problem remained. Ulysses proved that the sun looks different when measured from outside the planetary corridor. It also proved how difficult it is to keep an instrument there. The next challenge was no longer whether a polar perspective mattered. It was whether mission designers could obtain that perspective without sending every spacecraft to Jupiter first. Once Ulysses proved that the solar poles were scientifically important, the obvious response seemed simple. Send another spacecraft higher, give it cameras, and stay closer to the sun. That solution combines three demands that work against one another. A spacecraft must climb out of the ecliptic to see the poles clearly. It must approach the sun closely enough to resolve small structures. And it must survive long enough to watch those structures evolve through the solar cycle. Each requirement makes the others harder. Moving closer to the sun improves the view. The same telescope can distinguish finer details because the target feels more of its field of view. Particle instruments can sample the solar wind before its structures have expanded, mixed, and interacted across millions of kilometers. Magnetic measurements can be connected more directly to regions visible on the solar surface. But a close solar orbit also means high speed. Near perihelion, a spacecraft is falling deep into the sun's gravitational field. Its orbital velocity rises dramatically. That is precisely where changing inclination becomes most expensive. The closer the mission moves for better observations, the more costly it comes to rotate the orbit toward the poles. The scientific desire and the transportation requirement pull in opposite directions. Ulysses avoided part of this conflict by making its decisive turn at Jupiter. It gained a steep inclination, but the resulting orbit carried it far from the sun for much of each revolution. Its instruments could sample particles and magnetic fields across a broad range of distances and latitudes. Yet it could not produce detailed images of the polar surface. A camera aboard Ulysses would not have solved the problem by itself. From the distant parts of the orbit, the sun appeared too small for the kind of polar imaging researchers wanted. Nearer the sun, the spacecraft crossed high latitudes only during limited portions of a long journey. The mission had been optimized for direct samplings across the heliosphere, not sustained close observation of fine solar structures. A successor designed to image the poles needed a different compromise. Solar Orbiter approached the problem incrementally. Instead of traveling to Jupiter for one enormous deflection, it entered an elliptical orbit that repeatedly returns to Venus. Each close encounter changes the trajectory slightly. Over several flybys, those small changes accumulate, raising the spacecraft farther above and below the solar equator. The mission trades inclination for time. In March 2025, Solar Orbiter observed the Sun from roughly 17 degrees below its equatorial plane. That angle would seem modest beside the more than 80 degrees reached by Ulysses. Yet it was enough to produce the first clear spacecraft images of the Sun's south polar region from outside the usual ecliptic view. The achievement exposed how incomplete every previous full-disk image had been. From Earth and most solar observatories, the poles are seen at a severe angle. Surface features are compressed near the visible edge. Magnetic measurements become harder to interpret because instruments detect only part of the field's orientation. Structures overlap along the line of sight. The final few degrees around each pole remain poorly observed or must be reconstructed from incomplete data. Tilting the viewpoint by 17 degrees did not place Solar Orbiter directly above the pole. It did not reveal the region as a circular cap viewed straight down, but it reduced the geometric distortion enough for multiple instruments to examine same area in different ways. One instrument mapped visible light and magnetic properties at the photosphere. Another recorded extreme ultraviolet emission from hot plasma above the surface. A spectrograph separated particular wavelengths, allowing researchers to infer temperature, composition, and motion in the thin transition region between the lower atmosphere and the corona. Together, these measurements showed more than a new photograph. They connected the polar magnetic field with plasma structures and flows occurring above it. That connection is central to the solar cycle. Near the beginning of a cycle, the Sun's large-scale magnetic field resembles a distorted dipole, with one dominant polarity near each pole. As activity increases, newly emerging magnetic regions carry flux across the surface. The polar fields weaken, become disordered, and eventually reverse switch. The reversal does not happen as one clean global switch. Solar Orbiter's early polar observations found a complicated mixture of magnetic polarities around the South Pole. That complexity was expected during an active phase, but seeing it from an elevated angle allowed the structure to be mapped more directly. The new perspective could help determine how fragments of magnetic flux migrate, cancel, and rebuild the polar field that will influence the next solar cycle. The poles are not passive endpoints. They are part of the mechanism through which the Sun reorganizes its global magnetism. That makes them important for space weather forecasting. The strength and structure of the polar fields near solar minimum are used as indicators of how strong the following cycle may become. Yet those are among the most difficult magnetic regions to measure accurately from the ecliptic. A better view could improve the initial conditions fed into solar models. It cannot make the Sun perfectly predictable. This is where the simple answer fails again. One might expect that seeing the poles more clearly will reveal the full machinery of the cycle. But images alone do not show how magnetic fields extend through the corona or connect to the solar wind. Local measurements alone do not identify exactly where the sampled plasma left the surface. A mission needs both remote sensing and direct sampling, coordinated while the Sun evolves beneath it. Solar Orbiter carries both kinds of instruments, but it still occupies only one point in space. When it measures a parcel of solar wind, researchers must trace that material backward toward a possible source region. Models can estimate the connection, but the corona is dynamic. Field lines open, close, reconnect it, and shift. The Sun rotates while the plasma travels outward. A feature image the surface may change before its particles reach the spacecraft. The mission is therefore performing a reconstruction, not watching a perfectly labeled stream from origin to detector. Parker Solar's probe attacks the same problem from the opposite direction. It stays near the ecliptic but dives far deeper into the solar atmosphere. By June 2026, it had completed 28 close approaches, repeatedly passing about 6.2 million kilometers above the visible surface and reaching speeds near 687,000 kilometers per hour. Parker gains proximity rather than latitude. Its instruments measure fields, plasma, dust, and energetic particles where the solar wind is still being accelerated and structured. Its wide-field camera looks sideways through the corona and inner heliosphere. The spacecraft has crossed the Alphen critical surface. entering regions where magnetic disturbances can no longer propagate faster than the surrounding flow. But Parker does not look down on the poles. Its orbit remains close to the solar equatorial plane because the same Venus encounters used to shrink its orbit were designed primarily to remove orbital energy, not to create a large inclination. Solar Orbiter sees more of the missing geometry. Parker reaches more of the missing environment. Neither spacecraft alone performs both tasks at their most extreme. To send Parker's instrument package into a Ulysses, like polar orbit, while preserving its close perihelion, would require combining a deep solar dive with a major plane change. Near the Sun, the spacecraft would be moving at extraordinary speed, making the inclination change prohibitively expensive. Farther away, the turn would become cheaper, but the mission would then need another sequence of maneuvers to return to the inner corona. A Jupiter assist could produce high inclination, but Jupiter lies in the cold outer solar system. A spacecraft designed for intense solar heating would also need to survive years far from the Sun, where solar power is weak. Large arrays suitable for Jupiter would become difficult to protect near perihelion. A nuclear power source would add mass. Thermal shielding would add more. Instruments optimized for faint distant conditions would face a completely different environment close to the Sun. The spacecraft would be pulled between incompatible designs before it ever left Earth. Solar Orbiter's compromise is less extreme but more balanced. It approaches to about 0.28 astronomical units, close enough for high-resolution imaging without entering Parker's most severe thermal environment. Venus gradually increases the inclination, with mission architecture intended to reach roughly 24 degrees during its nominal high latitude phase and potentially about 33 degrees during an extended mission. That is still far short of a true polar orbit. At 33 degrees, the spacecraft will see the polar regions much more clearly than Earth-based observatories can, but it will not look straight down on them. Some projection effects will remain. Some structures on the far side of the pole will still be hidden. The improvement will be substantial, not complete. The mission is not failing to reach 90 degrees. It is selecting the portion of the view worth the cost. This is a recurring principle in spacecraft design. Scientific return rarely increases in proportion to difficulty. The first 17 degrees above the usual viewing plane can reveal information that was previously inaccessible. Reaching 33 degrees may improve that view further. The final climb toward 90 degrees could demand vastly more energy while producing a smaller additional gain for many instruments. The most dramatic trajectory is not automatically the best mission. Ulysses needed extreme latitude because its purpose was to sample the heliosphere across nearly the full range from south to north. Solar Orbiter can answer many polar questions from a moderate angle because it is looking at the Sun rather than trying to pass directly above every region it studies. Parker can investigate the birth of the solar wind without leaving the ecliptic because proximity gives it access to the flow before it evolves farther outward. The three missions occupy different compromises within the same physical constraint. One borrowed Jupiter's gravity to turn steeply. One borrows repeated encounters with Venus to climb gradually. One used Venus to surrender orbital energy and fall deeper toward the Sun. Together, they provide something no single trajectory could deliver economically: latitude, imaging, and proximity. The simple answer was to build one better polar spacecraft. The workable answer has been to distribute the problem among several missions, each accepting a different limitation. That solution changes the next question. If mission designers cannot afford every desirable trajectory at once, then the future of high-latitude exploration depends on finding new ways to alter velocity without carrying an impossible mass of propellant. The remaining options do not eliminate the price of the turn. They change what must be paid. Changing the price of a plane change begins with changing the propulsion system. Chemical rockets remain unmatched when a spacecraft needs a large amount of thrust in a short time. They lift payloads from Earth, escape planetary gravity, and perform urgent corrections. But their strength is also their limitation. They accelerate a relatively large mass of propellant to a relatively modest exhaust velocity, then consume it quickly. For a mission that must accumulate an enormous velocity change over years, that approach becomes punishing. The spacecraft is forced to carry propellant for future burns, propellant to accelerate that propellant, and structure strong enough to contain all of it. Electric propulsion reverses the balance. An ion or Hall effect thruster uses electrical energy to accelerate charged particles to exhaust velocities far beyond those of chemical engines. The thrust may be almost imperceptible, sometimes comparable to the weight of a few sheets of paper in Earth's gravity. But it can continue for thousands of hours. A weak engine operating for years can eventually produce a large change in velocity. This is not merely a slower version of a chemical burn. Continuous thrust changes how the trajectory itself is designed. Instead of coasting months between brief maneuvers, the spacecraft follows a path being reshaped almost constantly. The thrust direction must change as the vehicle moves around the Sun. At some points, the engine may raise or lower the orbit. At others, it may rotate the orbital plane. The mission becomes a long sequence of small vector adjustments rather than a few isolated events. In principle, this is well suited to climbing away from the ecliptic. The spacecraft does not attempt a 90-degree turn near Earth. It gradually tilts the orbit, adding a small vertical component during each revolution. Over time, those contributions accumulate. The propellant requirement can be far lower than for a chemical system. But the energy must come from somewhere. Close to the Sun, large solar arrays can produce potential electrical power. Yet the spacecraft is moving quickly, making each degree of inclination expensive. Far from the Sun, the orbital speed falls and the turn becomes cheaper. But sunlight weakens according to the inverse square law. At Jupiter's distance, a solar array receives only a small fraction of the energy available near Earth. At Saturn, the fraction is smaller still. The region where the maneuver is dynamically cheapest is also the region where solar electric propulsion becomes hardest to power. Larger arrays can compensate, but they increase mass. They must unfold reliably after launch and remain stable during years of thrusting. Their structure must survive vibration, thermal cycling, and repeated attitude changes. If the spacecraft later returns close to the Sun, those same arrays may need to be tilted away from intense sunlight or partially retracted. A design intended to operate in both the outer and inner solar system begins to pull itself apart. Nuclear electric power avoids the decline in sunlight. A radioisotope generator or reactor can supply energy regardless of distance from the Sun. That allows the spacecraft to thrust in the slow outer regions where inclination changes are cheaper. But the available electrical power is limited, especially for systems small enough to launch economically. High-power reactors require shield radiators, control equipment, and structures that add mass. Every kilogram added to the power system is a kilogram unavailable for instruments, propellant, communications, or protection. More power increases thrust. More power also increases the spacecraft that must be accelerated. Solar sails remove propellant from the equation entirely. A reflective sail receives a continuous push from sunlight. The pressure is weak, but it acts without consuming onboard reaction mass. By changing the sail's orientation, a spacecraft can alter the direction of that force and gradually reshape its orbit. For a high-inclination solar mission, a sail could spiral inward, where sunlight is stronger, then use the increased pressure to push the orbit out of the ecliptic. The closer approach provides more force. It also exposes the sail to greater heat and demands materials that remain reflective and stable under intense radiation. The sail must be large and extremely light. Its surface must retain the required shape. Small wrinkles, uneven reflectivity, or degradation can alter the thrust. The structure must control a membrane that may span hundreds or thousands of square meters while remaining thin enough to keep the acceleration useful. A sail avoids carrying propellant, but it replaces the fuel problem with a materials problem. Each technology moves the constraint rather than removing it. Electric propulsion trades thrust for time. Nuclear power trades sunlight dependencies for mass and complexity. Solar sails trade propellant for area, thermal tolerance, and control. Gravity assists trade onboard energy for planetary alignment. A future polar mission may need several of these methods at once. It might launch chemically from Earth, use a planetary flyby to reduce the largest part of the inclination cost, then continue with electric propulsion for years. A solar sail might supply part of the remaining change, while conventional thrusters handle precision navigation. The final trajectory would not be created by one breakthrough engine, but by a layered system in which each technology performs the part it handles most efficiently. That layering introduces new failure paths. A long-duration, low-thrust mission depends on engine lifetime. Thruster grids erode, cathodes degrade, power electronics experience radiation and thermal stress. A system that works for several thousand hours may not survive the tens of thousands required for a more ambitious trajectory. Continuous propulsion also demands continuous navigation. A spacecraft coasting between planets can tolerate periods of limited control. A vehicle slowly rotating its orbit must know its position, velocity, and thrust performance with high precision over long intervals. Small errors can accumulate. An engine producing slightly less thrust than expected for months may shift the arrival geometry by millions of kilometers. The mission can correct some errors, but every correction consumes margin. Communication becomes another constraint. A spacecraft far above the ecliptic may have an unusual line of sight to Earth, but distance still weakens the signal. If it travels far outward before making the turn, commands take tens of minutes or hours to arrive. The vehicle must handle faults autonomously. Autonomy reduces dependence on mission control, but it requires more software, more onboard processing, and more confidence that the spacecraft can distinguish a real emergency from a faulty sensor. A safe response may conflict with the trajectory. If the spacecraft enters a protective mode and stops thrusting for several days, it may miss part of a carefully timed maneuver. If it continues thrusting during a navigation error, it may amplify the problem. The control system must decide whether preserving the vehicle or preserving the higher priority. For missions lasting decades, reliability becomes inseparable from orbital mechanics. The longer route chosen to save propellant gives components more time to fail. Bearings wear. Detectors accumulate radiation damage. Redundant systems age even when unused. A mission that reaches a high-latitude orbit after 15 years may arrive with more direct mission that was never affordable to launch. Fuel efficiency can consume operational to life. There is also a scientific trade-off hidden inside the trajectory. A spacecraft sent far above the ecliptic gains a view unavailable near the planetary plane. It can measure the heliosphere at high latitude, observe the sun's poles, and studies distribution of dust and energetic particles away from the familiar corridor. But it leaves behind most planets, asteroids, and known small ball-body populations. Opportunities for secondary encounters decline. A mission within the ecliptic can often combine several investigations: a planetary flyby, measurements of dust, observations of moons, and gravity assists toward a later target. A steep polar trajectory passes through a region containing fewer reachable objects. The mission becomes scientifically specialized. That can make it harder to justify. A spacecraft expensive enough to leave the ecliptic may be expected to answer many questions. Yet the trajectory itself limits the number of targets it can visit. Adding instruments broadens the science but increases mass. Increasing mass reduces acceleration. Reduced acceleration lengthens the mission or lowers the final inclination. The payload competes directly with the orbit. This creates a design loop with no clean endpoint. More instruments increase scientific return, but reduce maneuvering performance. More power improves propulsion, but adds mass and heat. More shielding extends survival, but increases launch requirements. More redundancy lowers the risk of a single failure, but creates more hardware that can fail. The mission must stop optimizing before every problem has been solved. That is why the most credible future concepts rarely promise an immediate 90-degree solar orbit. They search for intermediate geometries with high scientific value, 30 degrees, 40 degrees, perhaps 60. They ask how much of the polar region becomes visible at each stage and how much direct sampling is gained. The final degrees may be the most expensive and the least necessary. A spacecraft does not need to hover exactly above the sun to transform our view of it. A moderate inclination sustained for several years may provide more useful data than a brief passage near 90 degrees. Continuous imaging, repeated latitude scans, and coordinations with spacecraft near the ecliptic can reconstruct a fuller three-dimensional picture than one dramatic polar flyby. The engineering objective is therefore not to go as high as possible. It is to buy the most valuable new perspective with the least destructive combination of mass, time, power, and risk. Ulysses paid with a journey to Jupiter. Solar Orbiter pays with repeated encounters and gradual ascent. A future mission may pay with decades of low thrust, a vast sail, a nuclear power system, or a payload reduced to a handful of essential instruments. The direction remains open. What changes from one generation of spacecraft to the next is the currency used to reach it. A spacecraft can reach a new viewing angle and still fail to see the thing scientists are trying to understand. The sun's magnetic field is invisible. The solar wind is nearly invisible. Much of the corona is so faint that direct sunlight must be blocked before its outer structure can be detected. The particles measured beside a spacecraft left the sun days earlier from a source region that has already rotated away or changed beyond recognition. The difficult trajectory only places an instrument where a measurement becomes possible. It does not make the measurement simple. Solar Orbiter's elevated view demonstrates the difference. From 17 degrees below the solar equator, its instruments could examine the south polar region with less distortion than any previous imaging spacecraft. But none of them recorded a complete self-explanatory picture. The polarimetric and helioseismic imager observes visible light from the photosphere, the layer usually treated as the sun's surface. It measures tiny changes in the polarization and wavelength of a specific iron absorption line. From those changes, researchers infer the direction and strength of magnetic fields and the motion of material along the instrument's line of sight. The resulting map is not a photograph of magnetism. It is a reconstruction derived from how magnetic fields alter light. That distinction becomes especially important near the poles. From Earth, polar magnetic fields are viewed almost edge-on. A field directed outward from the surface can lie nearly perpendicular to the observer's line of sight, making part of it difficult to measure. Features become compressed into a narrow region near the solar limb. Several structures at different depths can overlap in the same image. Researchers can correct some of this distortion mathematically, but corrections depend on assumptions. A map assembled from an unfavorable angle may look complete while containing regions where the uncertainty is much larger than the image suggests. Solar Orbiter improves the geometry. It does not eliminate the inference. Its extreme ultraviolet imager measures radiation emitted by plasma at particular temperatures in the upper solar atmosphere. Bright loops, compact eruptions, plumes, and darker regions reveal how hot material is distributed above the surface. But an ultraviolet image compresses a three-dimensional atmosphere into a two-dimensional frame. A bright feature may contain a long structure aligned with the line of sight, or a shorter, denser feature viewed from the side. Two unrelated loops can overlap. A dark area may represent lower density, lower temperature, different composition, or plasmas at the instrument's selected wavelength. Brightness is evidence, not a complete diagnosis. The SPICE spectrograph separates ultraviolet light into narrow wavelength bands produced by different ions. Each ion becomes abundant under a particular range of temperatures. By comparing these emissions, scientists can estimate temperature, density, composition, and movement through the transition region and lower corona. A slight wavelength shift can reveal plasma moving toward or away from the spacecraft. Yet, SPICE does not record the entire sun at one instant. It builds maps by scanning a narrow slit across the target. A complete image may combine observations made at different moments. The sun can change while the map is being assembled. A jet can brighten and fade. A magnetic structure can reconnect. Plasma can accelerate through the region. When the final scan is displayed as one frame, the image may appear to represent a single moment, even though different parts were measured at different times. That is not a flaw unique to SPICE. It is a general problem in observing a large dynamic object with limited instruments and limited data rates. Greater spatial detail usually requires a smaller field of view, a slower scan, or more information than the spacecraft can immediately transmit. Every instrument chooses what to discard. A detector may record a narrow range of wavelengths and ignore the rest. A camera may compress images before sending them to Earth. A particle instrument may group measurements into time intervals. During periods when the spacecraft is behind the Sun or operating near perihelion, detailed data can remain stored on board until communication conditions improve. The final scientific record is shaped partly by physics and partly by bandwidth. Remote sensing instruments reveal what is happening at a distance. In situ instruments measure what reaches the spacecraft itself. The two approaches answer different questions. A camera can identify a dark coronal hole that may be releasing fast solar wind. A magnetometer can measure the field carried past the spacecraft. A plasma analyzer can determine the speed, density, temperature, and composition of the arriving particles. Connecting those observations requires tracing the flow backward. The simplest reconstruction assumes that plasma travels radially outward while the Sun rotates beneath it. From the measured speed and the spacecraft's location, researchers estimate when the material left the corona and which longitude faced the spacecraft at that time. The real path is more complicated. Magnetic field lines curve into spirals. The solar wind accelerates before reaching its final speed. Fast streams overtake slower ones. Waves and turbulence alter particle motion. While the material is trapped, evolve. Magnetic connections can change while the material is traveling outward. The spacecraft can measure a parcel with extraordinary precision and still face uncertainty about where it originated. This is one reason coordinated observations are so valuable. Parker Solar Probe can sample plasma close to the Sun before it has undergone as much mixing. Solar Orbiter can image possible source regions from an elevated angle. Spacecraft near Earth can measure how the same large-scale structure evolves farther outward. Ground-based telescopes and observatories in Earth orbit provide continuous views when distant spacecraft cannot transmit or when their instruments are pointed elsewhere. No instrument produces the global answer. The answer emerges from comparison. Even then, simultaneity is limited. Light reaches each observer at slightly different times. Plasma reaches them much later. The spacecraft occupy different longitudes, latitudes, and distances. A structure measured by Parker near the Sun may rotate, expand, and interact with other flows before a related signature reaches solar orbiter or Earth. Researchers do not merely combine measurements. They combine measurements with models of what happened between them. The models are tested by whether they predict later observations. When a simulated magnetic connection identifies the wrong source region, or when a modeled solar wind stream arrives too early, too late, or with the wrong composition, the disagreement exposes missing physics or incorrect assumptions. Observation and interpretation advance together. The polar regions contain another measurement problem because the Sun's interior cannot be seen directly. Motions beneath the photosphere must be inferred through helioseismology, which studies waves traveling through the solar interior. Millions of oscillations continually ripple across the surface. Their frequencies and travel times are altered by temperature, rotation, and flows beneath them. By measuring those changes, scientists can reconstruct parts of the internal structure, much as seismic waves reveal Earth's interior. Near the poles, the geometry again becomes difficult. Surface motions are foreshortened when viewed from the ecliptic. Signals weaken. Some wave paths are poorly sampled. Elevated observations may improve the measurements and help determine how internal circulation transports magnetic flux toward the poles. But a 17-degree view remains far from looking there straight down. The most difficult region is better exposed, not fully revealed. A true polar observatory could reduce these limitations. It could monitor magnetic evolution with less projection distortion, follow the growth and disappearance of polar coronal holes, and improve measurements of flows linked to the solar cycle. It would still observe only the hemisphere facing it. The Sun rotates, so most regions eventually come into view. But rapidly changing events cannot always be reconstructed from delayed observations. A spacecraft above one pole cannot see the opposite pole directly. One above the north would not provide us simultaneous face-on view of the south. Complete coverage would require multiple observers, perhaps at different latitudes and longitudes operating at the same time. That multiplies the engineering problem. Each spacecraft needs power, communications, thermal protection, navigation, and instruments. Their observations must be calibrated against one another. Slight differences between detectors can imitate real changes in the sun. Clocks must be synchronized. Data formats must be compatible. The network must remain scientifically useful when one vehicle enters safe mode or loses contact. A three-dimensional observatory is not one spacecraft in an unusual orbit. It is a system distributed through space. For now, scientists work with an incomplete network. Ulysses supplied high-latitude particle measurements without polar images. Solar Orbiter supplies elevated imaging and local sampling from moderate inclinations. Parker reaches the near-Sun environment from close to the ecliptic. Other observatories provide continuous context from farther away. Their strengths overlap, but they do not close every gap. This is the deeper value of leaving the planetary plane. The new angles does not simply make the Sun look different. It changes which quantities can be measured reliably, which ambiguities can be reduced, and which assumptions can finally be tested against observations. It also reveals how much remains inferred. The polar magnetic field, the origin of the fast solar wind, the transport of flux across the surface, and the changing three-dimensional shape of the heliosphere are no longer hidden in the same way they were before Ulysses. Yet none has become a completed map. The observational frontier is not defined by whether light or particles exist to be detected. It is defined by whether an instrument can reach the right place, at the right time, with the right orientation, and connect what it records to a system changing faster than the map can be assembled. After decades of polar passes, close solar encounters, and increasingly elevated views, the evidence is finally broad enough to support a more complete answer. Not a final picture of the Sun, but the best three-dimensional model current observations can defend. The best current answer begins with a distinction that ordinary language usually hides. A spacecraft can rotate its body almost effortlessly. It cannot rotate its orbit without paying for the difference between two velocity vectors. That is why the empty space above the ecliptic is dynamically distant even when nothing physical blocks it. The difficulty does not come from a wall, a boundary, or a force pushing spacecraft back toward the planetary plane. It comes from the speed they already possess. Anything launched from Earth begins by sharing Earth's motion around the Sun. Nearly 30 kilometers per second of sideways velocity is present before the mission adds its first heliocentric maneuver. That motion is useful for reaching destinations that also orbit near the ecliptic. It becomes expensive when desired path points far away from that plane. The controlling quantity is not altitude. It is angular change multiplied by orbital speed. A small inclination correction can be manageable. A large one near Earth is not, in the idealized case of preserving speed while rotating a circular solar orbit through 90 degrees. The required velocity change is about 42 kilometers per second. The same spacecraft needs only about 12 kilometers per second of additional heliocentric speed to reach solar escape from Earth's distance. The comparison does not describe a complete launch from Earth. It isolates the orbital problem. And it explains the apparent paradox. Moving permanently away from the Sun can require less velocity change than turning a solar orbit through a right angle. The route becomes cheaper only when one of the terms changes. The spacecraft can make a smaller turn. It can perform the turn where it is moving more slowly. It can divide the maneuver across many years. Or it can obtain the deflection from another body instead of carrying all the required propellant. Every successful high-latitude mission has used one or more of those strategies. Ulysses traveled to Jupiter, where the geometry and lower heliocentric speed made a radical redirection possible. Jupiter's gravity supplied the decisive bend. The result was an orbit reaching more than 80 degrees of solar latitude, sufficient to measure the solar wind and magnetic environment above both poles. Solar Orbiter accepts a much smaller inclination. Repeated Venus encounters raised the angle gradually, placing the spacecraft high enough to reduce the severe projection effects that had hidden the polar regions from previous imaging observatories. In March 2025, from about 17 degrees below the solar equator, it obtained the first clear spacecraft views of the Sun's south pole. Parker's solar probe solves a different part of the problem. It remains near the ecliptic but travels deep into the corona. repeatedly sampling the solar wind close to where it forms. Its trajectory sacrifices latitude for proximity. Together, these missions reveal the practical answer more clearly than any one of them could. There is no single best orbit for studying the Sun. A steeply inclined orbit provides latitude, but usually sacrifices closeness, payload, or mission time. A close equatorial orbit reaches the source environment, but retains a distorted view of the poles. A moderate inclination with the imaging instruments may answer many polar questions without paying for the final climb toward 90 degrees. The value of a trajectory depends on the measurement, not on how dramatic the orbit looks. This is why future polar exploration is unlikely to be defined by one spacecraft simply repeating Ulysses with a larger rocket. The more credible architecture is a network of complementary observers, one or more spacecraft at elevated latitudes, probes close to the Sun, and observatories near Earth or elsewhere in the ecliptic. Their measurements can be combined to reconstruct a changing three-dimensional heliosphere. Even that reconstruction will remain incomplete. The solar wind measured beside a spacecraft left the Sun earlier. Its source region may have rotated, evolved, or reconnected magnetically before the particles arrived. Images compress three-dimensional structures into two dimensions. Magnetic maps depend on how light is altered by fields along a line of sight. Spectral scans assemble different parts of the Sun at different moments. A new angle reduces estimate inference. The best current model is therefore not a static globe surrounded by a uniform wind. It is a variable magnetic system whose structure depends on latitude, longitude, distance, and phase of the solar cycle. Near solar minimum, large polar coronal holes can produce broad regions of fast, relatively steady wind. Slower and more variable flows dominate closer to the equatorial belt, where fast plasma overtakes slower plasma. Enormous compression regions form and propagate outward. Near solar maximum, that order division weakens. Magnetic polarities become mixed at the poles. Active regions appear across a wider range of latitudes. Eruptions and irregular losses disturb much more of the heliosphere. The global field reverses, then gradually rebuilds into a new configuration. The polar regions are central to that reorganization. They are not merely remote caps added to an otherwise complete solar map. Magnetic flux transported across the surface accumulates, cancels, and eventually establishes the polar fields that help shape the next activity cycle. Measuring those fields accurately may improve forecasts of the Sun's future behavior, but the relationship is not a perfect clock. Models still differ in how they represent flows beneath the surface, the emergence of new magnetic regions, and the movement of flux toward the poles. The Sun is predictable in patterns and difficult in details. That uncertainty gives the expensive term its scientific value. High-latitude observations test whether models developed from the ecliptic describe the rest of the system. Ulysses found that several simple expectations did not. The fast wind occupied a much larger polar region than familiar near-Earth measurements suggested. Open magnetic flux appeared more uniform with latitude than basic models predicted. Cosmic rays did not stream inward through the poles as freely as an uncomplicated magnetic geometry implied. Solar Orbiter has now added direct polar imaging to that evidence. Its first elevated maps showed Mixtet's magnetic polarity, extending to the South Pole during the reversal phase of the cycle. Ultraviolet observations revealed hot plasma structures from a perspective never previously available to an imaging spacecraft, while atmospheric instruments mapped the surface below. These observations do not finish the polar map. They show which parts of the old map construct hid essential geometry. The transportation problem and the scientific problem are therefore the same problem viewed from opposite problem. The ecliptic is convenient viewed from opposite side. The ecliptic's inherent motion within it, launches inherent motion within it, and gravity assists are available there. The same convenience creates an observational bias. Most spacecraft measures a solar system from the corridor that is easiest to travel through. What we know best is partly what orbital mechanics made affordable. Leaving that corridor is expensive, but the expense is not evidence of a natural prohibition. It is the accumulated consequence of the solar system's formation. The protoplanetary disk gave the planets a common direction of motion. Earth passes that motion to every spacecraft. Rocket propulsion makes large changes costly. Planetary gravity offers rare opportunities to redirect the inherited path. The vanished disk survives as both a transportation system and a blind spot. The strongest answer available today is therefore not that spacecraft cannot go up. They can. And several have moved far enough above the familiar plane to transform solar science. The answer is that a spacecraft never begins from rest. Direction cannot be changed for free, and the planets that could help are concentrated in the very plane the mission is trying to leave. The most effective solution is not to overpower that architecture. It is to use it selectively. Travel outward before turning, borrow momentum from a planet, thrust gently for years, accept a moderate inclination, or combine observations from several incomplete trajectories. Physics does not close the direction. It forces every mission to decide how much of that direction is worth buying. At Jupiter, Ulysses made a turn no rocket could afford to make alone. For a few hours, the spacecraft passed through the gravitational influence of a planet more than 300 times the mass of Earth. It arrived moving through the same broad plane as the worlds that had carried it there. It left on an orbit tilted almost upright against them. The maneuver looked like an escape from the architecture of the solar system. It was actually a product of that architecture. Ulysses could leave the planetary plane only because Earth had launched it with inherited orbital speed, because Jupiter occupied a reachable path within the same plane, because the giant planet carried enormous momentum around the Sun, and because mission designers could arrange the encounter so that a small part of that motion was transferred into a new direction. The spacecraft did not defeat the system that constrained it. It used the system once, with extraordinary precision, to reach a place the ordinary routes could not provide. That is the central answer. The most expensive turn in the solar system is expensive because a spacecraft is never choosing a direction from rest. It begins inside moving structure. Earth already travels around the Sun at nearly 30 kilometers per second. A departing vehicle inherits that motion. To move toward another planet, outward toward interstellar space, or inward toward the Sun, the mission can often reshape the orbit while preserving much of that existing velocity. To move steeply above or below the planets, it must rotate the velocity itself. The difference is not visible on a conventional map. A map shows empty space surrounding the Sun in every direction. It suggests that all routes are equally open. But orbital mechanics is not a map of empty space. It is a map of moving states. Each planet occupies a position and carries a velocity. Each spacecraft departs with a velocity. Every destination requires another. The true distance between two trajectories is measured partly in kilometers and partly in how much motion must be changed to connect them. That is why a spacecraft can escape the Sun more cheaply than it can turn through 90 degrees near Earth's orbit. Escaping builds on motion already pointing in a useful direction. A right-angle plane change attempts to replace that direction almost entirely. The distinction reaches back to the formation of the solar system. The young planetary system became flat because collisions within a rotating cloud gradually removed much of the motion above and below the emerging diskek. The remaining material continued circulating around the center, carrying angular momentum that could not simply disappear. The planets formed from that shared flow and preserved it in their orbits. The original gas disk is gone. Its motion remains. It remains in Earth's path around the Sun. It remains in the narrow range of planetary inclinations. It remains in the gravity assist corridors used by Voyager, Parker Solar Probe, Solar Orbiter, and countless other missions. It remains in the launch windows, calculated years in advance, and in the fuel margins that decide whether a spacecraft can carry another instrument. The ancient disk became an invisible transportation network. Most missions stay close to it because that is where the destinations are, where planetary gravity can be borrowed, and where inherited velocity can be used rather than erased. The same geometry that makes interplanetary travel possible also confines most exploration to one thin region. That confinement has shaped knowledge. Before Ulysses, direct measurements of the solar wind came solely from near the ecliptic. The heliosphere was interpreted through observations taken along the easiest routes. Once a spacecraft finally crossed the high solar latitudes, the picture changed. The polar wind proved faster and more uniform during solar minimum than the familiar wind near the equator. Open magnetic flux did not vary with latitude in the simplest expected way. Cosmic rays did not find an uncomplicated entrance through the poles. Later passages showed that the ordered polar structure could break down as the sun approached maximum activity. The missing angle contained missing physics. Solar Orbiter is now extending that view with images. It has begun to reduce the distortion that made the polar regions difficult to map from Earth's neighborhood. Its inclination is far below the near polar path of Ulysses. Yet even a moderate elevation reveals magnetic and atmospheric structures that the ecliptic compresses against the edge of the sun. That result carries an important correction. The goal is not always to reach the most extreme possible orbit. A spacecraft at 30 degrees may answer questions that once seemed to require 90. A network of incomplete viewpoints may reveal more than a single dramatic trajectory. Parker Solar Probe can investigate plasma close to its source while remaining near the ecliptic. Solar Orbiter can connect elevated images with local measurements. Observatories near Earth can monitor the wider solar disk continuously. Together, they can reconstruct a system none can observe alone. Exploration advances by choosing the right limitation. A mission can spend fuel, time, payload, power, or dependence on planetary alignment. It cannot eliminate every cost. A larger propulsion system reduces the mass available for instruments. A slower, low-thrust route preserves propellant while consuming years of operational life. A solar sail avoids reaction mass, but requires enormous, delicate material. A Jupiter assist provides a powerful bend, but forces the mission to travel far from the sun before returning. Every solution changes the currency. Future spacecraft may climb higher than Ulysses. Electric propulsion could accumulate inclination over long periods. Solar sails may use intense sunlight close to the sun to rotate and orbit gradually. Nuclear electric systems could continue thrusting where solar power becomes weak. New combinations of flybys and propulsion may create trajectories that are currently too slow or too expensive. But none of those technologies will make direction free. They will succeed by recognizing the same fact Ulysses revealed. Velocity is part of the environment. Motion is not an inconvenience added to the solar system. It is the structure of the solar system. That changes the meaning of the original image. A spacecraft above the planetary plane would not be standing over a motionless diagram. Below it, the planets would be circling the sun at different speeds. Asteroids would trace overlapping paths. Dust would spiral under radiation pressure and drag. Comets would cut path in changing streams. The solar wind would expand in changing streams, carrying magnetic fields outward into interstellar space. The disk would not look like a surface. It would look like a memory in motion. From far enough above, the major planets might appear to occupy a narrow band, but the solar system would not end there. Scattered objects would extend beyond Neptune on inclined orbits. Long-period comets would arrive from the roughly spherical reservoir inferred to surround the distant sun. The heliosphere itself would be shaped by the sun's motion through the local interstellar medium rather than by the ecliptic alone. Even the highest possible view would not produce a final map. It would only replace one incomplete perspective with another. That is why difficult turn matters. It is not valuable because up is a special cosmic direction. There is no universal up. It is valuable because changing the angle changes the evidence. The planetary plane gives us access to worlds. Leaving it gives us access to assumptions. Ulysses traveled to Jupiter because the shortest looking route was physically unaffordable. It moved outward before it could move upward. It borrowed the momentum of a giant planet, crossed the high latitudes of the sun, and returned data from a heliosphere more structured than the equatorial view had implied. The mission's deepest result was not a single measurement. It was a demonstration that the easiest path through a system can become the narrowest way of understanding it. Today, most spacecraft still travel inside the ancient corridor. They follow the motion left behind by a cloud that collapsed more than 4.5 billion years ago. They use that motion to reach planets, moons, asteroids, and the space beyond the heliosphere. A few attempt the turn. They do it slowly, indirectly, or by borrowing the force of a world. And each time one succeeds, the solar system becomes slightly less flat, not in its physical shape, But in the map we are finally able to make of it,